Swayam Prabha. Digital India. Educated India.
Okay, so let me have your attention. So let's get back to this derivation that we were doing, which was basically trying to show that there really exists a circle of curvature and a center of curvature. And so what we have done is that basically we have taken a point on a curve and you have taken a nearby point, okay, and taken the normals, okay, and then you have taken the intersection point of the normals, and you show that this intersection, the x and y coordinate, they go to a limit as the nearby point approaches the given point, okay. So what we have done is we have actually derived the x coordinate, okay. So let me show you that. So this picture, this picture needs to be drawn far better, in the sense that the curve. Let me just correct this picture a little bit. Uh, so you see the curve, which is gamma t. The if you look at it, the way I've drawn it, this is the curve, okay, and the red one is the the circle of curvature, and it doesn't look nice, and certainly doesn't look like it's approximating it. So the correct thing is, uh, I redraw this curve again, the curve part. Uh, So you see, the curve should rather be, something like this. You know, um, the curve should be something like this. Okay, this must be my gamma t, right? And so basically, what we have done is, we have taken the uh, um, uh, we have got this point, which is the center of curvature. The center of curvature of the curve for the given point p naught on the curve, which corresponds to t equal to t naught. That means p naught is gamma of t naught, okay. And the c of p naught with the center of curvature at p naught actually has an x coordinate and the y coordinate, all right. And we wrote out the x coordinate. I haven't written out the y coordinate, and at least if you look at it as vectors, it's kind of clear how the coordinates of C P naught should be. This being the origin here, okay. So you have this vector, which is the position vector of C P naught, and P naught is supposed to be at t equal to t naught, okay. So that vector I have called it as epsilon sub t naught or epsilon sub p naught, and the reason why I have used epsilon is because that is the position vector of the center of curvature, and I told you that as the point moves on the curve, depending on how the curve is curving, the centers of curvature will also move, and they will trace a locus, and that's called the evolute. That is the reason that I have called so as t varies, this when t equal to t naught, you are reading Cp naught, okay. If so this Cp naught can also be thought of as C depending on t naught, and now if t naught is going to be replaced by t, then you will get Ct, which is the center of curvature for the point gamma t on the curve, and as t varies, this Ct will trace a locus. That will be the evolute of the curve, okay. The evolute of the curve is just the loci of the centers of curvature, all right. So that's the reason why I gave this notation epsilon t naught, and you can see by the triangle law of addition, this epsilon t naught is actually this position vector gamma t naught, okay, added with this normal vector, unit normal vector, multiplied by this radius of curvature, which is actually this vector, okay, which is this vector, okay, by the triangle law. And of course, the question was, how do you get this unit normal vector? And I told you that if at least the direction of the tangent vector is kind of fixed for a curve once you give a parametrization for increasing values of the parameter, okay, the point on the curve is traversed in a certain way, so that gives the orientation of the curve. So whenever you parametrize a curve, the parametrization will automatically give an orientation, all right. And because you have a direction on the curve, that means that at every point of the curve you have the direction of the tangent vector, all right. Otherwise, if we give a point on a curve, you will only get a tangent line, and it has two directions, two opposite directions, okay. But if you want a particular direction, you need to say whether you are going in one direction or the other on the curve, and that is given by the orientation, all right. So therefore, the tangent vector is well defined. The problem is that the normal vector is not well defined because you have two normals in two opposite directions. The normal line is well defined, but there are two vectors on in the two opposing directions. So the question is, which one do you choose? And that is where I told you that we have to use the idea of what is called a signed normal. The signed normal is you take the tangent vector is already given, you rotate it by anti-clockwise by 90 degrees, and whatever direction you get, that should be the direction of the signed normal. Okay, so that is the convention. And then you can see that you can write out this this diagram, which is addition of vectors in the following way: epsilon t naught is gamma vector. Now you see there is this dual point of view, that any point on the plane you either think of it as two coordinates or you think of it as position vector with respect to the origin. Okay, so in that sense, this epsilon vector, which is the position vector of the center of curvature, is the gamma vector, which is the position vector of the point on the curve, plus this vector in the normal direction, the signed normal direction, and the length is of course the radius of curvature. Okay, and this is something that doesn't need anything. It is just if you believe that there exists a circle of curvature, then you can write this down. This is just triangle law of addition of vectors. The question is, you have to find expressions for the radius of curvature and the coordinates of center of curvature. Okay, and that's what we did. We used calculus, and we got two equations, one for the normal at that point and for a nearby normal, and then we took the point of intersection and then showed that the point of intersection, which has two coordinates, x coordinate and y coordinate, they tend to a limit giving the center of curvature as the nearby point approaches the point on the curve. Okay, and we got this. So I'll show you so this was the expression that we got after taking the limit. Okay, and this expression in terms of addition of vectors, this vector, if you this if you write it in terms of scalar components, then you get the x component gives you this. Okay, and if you compare these two, the claim was that you can easily write out what is the radius of curvature and what is the center of curvature. So for the moment, I mentioned that this is what you are supposed to get, and that is quite easy to see. This is the expression that you get by vector addition, the x component, and this is the expression that we got by taking a limit. Okay, so I'll just say that this is gotten by limiting process. Okay, and you see now if you remember, you see our so let us make this computation. See, our m dot, the m was supposed to be the slope of the normal. Okay, see the position vector or the point on the curve is given by xt comma yt. Okay, the tangent vector is given by gamma dot, which is going to be x dot t and comma y dot t, where dot denotes derivative with respect to t, d by dt. All right, and the slope of the tangent will be y dot by x dot, and therefore the slope of the normal is a negative reciprocal of that. So this m will be, so m is m of t actually. Okay, and this is going to be minus x dot by y dot. This is what your m is. And then I told you m naught is, it means that you have to do it at t equal to t naught, or take limit at t equal to t naught. Substituting t equal to t naught and taking limit at t equal to t naught, they are the same because of continuity. We are assuming always continuity. Okay, so m naught is going to be minus x naught dot by y naught dot. Okay, so you have to plug that in here. So look at this this expression gotten by the limiting process. You plug it in here. So what happens is that you will get. So let me write this. So let me erase this and write it here. So this is going to be x dot. I mean this is x naught plus y dot squared. Okay, by this expression which is x naught dot y naught double dot minus y naught dot x naught double dot. That is the expression below. M naught is going to be this, so you plug this in. Okay, so I will get minus x naught dot by y naught dot times x naught dot. Okay, so let me write that carefully. Okay, that is this, and then I have a minus y naught dot. Okay, and if you simplify this, what is it you are going to get? So you see, you will get x naught, and then there is a minus sign, minus y naught dot squared, and inside I am going to get x naught dot squared plus y naught dot squared. Okay, divided by x naught dot y naught double dot minus y naught dot x naught dot. Okay, this is what I am getting. All right, and now you see this is the x coordinate of the center of curvature. All right, and similarly, if you if you write out the so I hope I have not I see I have to cancel out one y naught dot, right? I have to do that. Yeah, so there is a y naught dot that I have to cancel out. So let me do that. So there is a y naught dot I have to cancel out. So that goes away. So this is what I get. All right, so let me write it again here. You see, x coordinate Cp naught, our center of curvature for the point P naught is x naught minus y naught dot times this expression x naught dot squared plus y naught dot squared by x naught dot y naught double dot uh, uh, just let me be careful. Um, yeah, so I'll get minus y naught dot x naught double dot. Okay, you will get this. So this is what it simplifies to. All right. Now you see what will happen to the y Cp naught. Okay, and what will happen to the y Cp naught is that you are going to get so this is something that one has to compute, and so I think I can compute it by plugging it in one of the equations. So you see, so what is it? So let's write it out. So you see, you have this normal. So this is the circle of curvature at P naught. This is the point P naught. Okay, and this is the center of curvature at this is Cp naught. So this is center of curvature. And this is circle of curvature. I mean at P naught, of course. At P naught, and then this length is the radius of curvature at P naught, r sub P naught. All right, that is this length. That is the radius of the circle, and then of course you have this curve going like so. You have this curve going very close to the. So this is your gamma t. Okay, and P naught is gamma of T naught. Okay, so this is the picture, and this P naught has coordinates x of T naught, which is x naught, and y naught. Okay, x naught is just x of T naught, and y naught is y of T naught. Okay, and so you see, if you calculate this, so so the normal direction is going to be minus x naught dot by y naught dot, okay, and that is the normal direction, and therefore this straight line passes through x naught y naught, all right, and so you know the equation of the straight line which is a normal. In that you substitute this x cp naught, you should get y cp naught, okay, so it's obvious. So you know, so let me write this out. If you write it out using the 2-point form, you will get essentially the following. Uh, you know, y cp naught minus y naught by x cp naught minus x naught is going to be the slope of that, which is minus x naught dot by y naught dot. So let us simplify this to get y cp naught. So you see y cp naught minus y naught is minus x naught dot by y naught dot x cp naught minus x naught, okay. So let me plug this in. So it is minus x naught dot by y naught dot, okay. Now this x cp naught value I have here, so let me plug it. It's x naught minus y naught dot times, in the numerator I have x naught dot squared plus y naught dot squared divided by the denominator I have x naught dot y naught double dot minus y naught dot x naught double dot. This is what it is. I end up with so plus x naught dot y naught dot and then there is a y naught dot in the denominator, and then I'll get x naught dot squared plus y naught dot squared by x naught dot y naught double dot minus y naught dot x naught double dot, and this is x y naught dot is going to get cancelled. Of course, whenever I am cancelling, you know, I am assuming that is not 0, and you are going to see that that will have that will eventually be an important condition later on, okay. So this is y cp naught minus y naught, so you will get y cp naught is equal to y naught plus this quantity x naught dot into x naught dot squared plus y naught dot squared divided by x naught dot y naught double dot minus y naught dot x naught double dot, okay. And now you see this is the y coordinate, okay. And if you now you know I have got the x coordinate, and so this is the x coordinate, okay, of the center of curvature, and this is the y coordinate of the center of curvature, okay. Now I want to write out the you know, in vector form and compare it with the equation that you got from the triangle law of addition, okay. That is what will give you the radius of curvature, okay. So put these two together, x cp naught y cp naught, so x cp naught y cp naught, add this, okay. Then you know I mean add it means not add it, put them side by side, okay. Then you see the first component is x naught here, okay, and here you are getting a y naught, all right, okay. So so I should write you know x naught comma y naught plus, okay, then, okay. So think of this as addition of vectors, you know I mean comparing two vectors component wise and addition of vectors component wise. So then the next term is going to be, you know, the x component is going to be this. So it will be minus y naught into this expression x naught dot squared plus y naught dot squared by x naught double dot x naught dot y naught double dot minus y naught dot x naught double dot. This is one term, okay, and the other term will be x naught. So here there's some is there a dot there or yeah. I suspect that there is a, so this was a y naught dot, so let me write it correctly. So here I'll get a x naught dot, that is just this term here that I am writing, x naught dot squared plus y naught dot squared divided by x naught dot y naught double dot minus y naught dot x naught double dot, okay. So all this looks very tedious, okay, with all these dots fooling around, okay, but the point is that finally it all will come down to something very nice from this. See, the point is this is a very raw calculation, okay, which is completely doable bare hands. And it's of course looks messy, all right. But the point is that it all from this you learn two or three, I mean three important things. One is you will see more or less, you will directly see the formula for general curvature, okay, in a very nice form. Then you will also get the formula for radius of curvature. You will also see that to get hold of all these formulas, you need second continuous differentiability. You need the fact that both the tangent vector should never be 0. Okay, you see all those things will come up. Okay, and they are going to be important in what we are going to do, which is actually trying to define curvature independent of the parametrization. So you must understand, all the pain is that you see curvature, suppose I want curvature of a curve at a point, I parameterize it. See, what I have done is I have parameterized it. So I have written it as gamma t. Then what I have done is I have done this limiting process and I have managed to find the center of curvature. Okay. Now how much do you think the this center of curvature and radius of curvature and circle of curvature should depend on the parametrization? See, after all, these are all geometric things. No matter how you parameterize the curve, these things should not change. Okay, the center of curve, it doesn't matter how you write the equation of the curve. The center of curvature, radius of curvature, circle of curvature, they are geometric things. They should not depend on parametrization. So you see, there is this. You have to do this reconciliation between the geometric things, which have got nothing to do with how the curve is written analytically. Okay, so there is some work to be done. Okay, so it's all geared towards that. So let us interpret this. So you see, let us again, the picture is like this. There is this vector which is epsilon at t naught, and this point is exactly this point. Okay, and then there is this point which is this point. This is just gamma t. This is just gamma t naught. This is just gamma t naught, and this is just epsilon t naught. Okay, that's what it is. If you write the vector as a pair of components, all right. And then what is this fellow here? So I am interested in this fellow. So you see, this is gamma t naught, and this fellow here, I told you, is the signed unit normal times radius of curvature. So you see, this fellow is going to be ns. So I will use subscript s to say signed unit normal at t naught. Okay, and I will put a cap to say that this a unit vector. Okay, by the way, epsilon t naught and gamma t naught are also vectors. I am not putting arrows on top of them as you do usually. It is to be understood. Okay, but here I am putting a cap because I want to stress that it is a unit vector. Then this times the radius of curvature at t naught. So this length here is r t naught. Okay, and this is just a triangle law. I want you to compare this expression that we have gotten by a limit with this expression. Okay, and you see, watch carefully. This fellow is, this is a scalar. Okay, this is a common scalar that is multiplied to both coordinates. Pull it out. If you pull it out, this fellow alone will become x naught dot squared plus y naught dot squared divided by x naught dot y naught double dot. So let me just write it. X naught dot y naught double dot minus y naught dot x naught double dot. Okay, times if you take the scalar out. Okay, this is just scalar multiplication of a vector. Okay, multiplying a vector by a scalar is the same as multiplying every component by that scalar. So I am just taking the scalar out. Okay, and here I will get minus y naught dot comma x naught dot. But what is this minus y naught dot comma x naught dot? Is exactly the sine normal. See, x naught dot y naught dot is the tangent. You rotate it by 90 degrees, you will get minus y naught dot x naught dot, and this is exactly the sine normal, but it is not the signed unit normal. If you want the signed unit normal, what you have to do is you have to divide by the length. Therefore, I have to, if I divide by root of x naught dot squared plus y naught dot squared, then this fellow is exactly the signed unit normal. Okay, and because I divided by this, I have to multiply here by root of x naught dot squared plus y naught dot squared. So this is what I get here. So now you see, you compare this equation, okay, with this term replaced by this. Okay, with the equation you get here by triangle addition, which is epsilon T naught is equal to gamma T naught plus R T naught into ns hat of T naught, and you will see immediately this radius of curvature is exactly this term. Okay, everything matches, and you see therefore the the radius of curvature at T naught is exactly, so you see this is a power half, this is a power 1, so it is x naught dot squared plus y naught dot squared to the power of 3 by 2 divided by x naught dot y naught double dot minus y naught dot x naught double dot, but there is a small glitch. The glitch is radius of curvature is positive. Therefore, what I have to do is that I have to put a mod here. All right. If I put a mod here, then there is a problem that there is a plus or minus, and that plus or minus is going to that you will have to worry about this plus or minus here. Okay. Therefore, what it means, why this plus or minus is coming is because what would have happened is, depending on how you are traversing the curve and whether the curve is concave or convex, the signed normal can point away from the center of curvature, or it can point towards the center of curvature, and you have to make a sign adjustment to the curvature itself for this equation to be correct. Okay. See, the tangent direction is fixed, and then you rotate it by 90 degrees anti-clockwise, the sign normal is fixed. Okay. Therefore, the sign, you don't know what is going to happen. Therefore, the only term you can adjust is the curvature term, and so you have to make the curvature into a signed curvature. So, this term can turn out to be negative. If it turns out to be negative, you have to call that the curvature, but it's negative, so it's called the signed curvature. So I'll tell you what is I'll tell you what are the 4 possible cases. See, you may have a curve being traversed like this. So at this point, you see you have the tangent at T naught. Okay, and then the signed normal will be like this. Okay, and this is because rotation by 90 degrees in the anti-clockwise sense. And now you see, if you draw the circle of curvature, the circle of curvature will be like this, and you see the signed normal is pointing towards the center of curvature. So in this case, the signed curvature is positive. Okay, so this is, so we introduce Ks. By the way, I should tell you, unsigned curvature, what is it? We have already agreed that it is a reciprocal of the radius of curvature. The larger the radius of curvature, the smaller the curvature, and the smaller the radius of curvature, larger the curvature. So our curvature is supposed to be reciprocal of radius of curvature. So unsigned curvature is written as just kappa, and it is just 1 by RT naught. This is unsigned curvature. If I say at T naught, I have to put kappa T naught, and this is just 1 by RT naught. Okay, and therefore you see, when if I want to replace this term by curvature, I have to write 1 by k, but then the problem is it may be a negative term, in which case I have to write actually 1 by k with k negative. So I have to put a sign to the curvature, and this is what is called a signed curvature. Okay, and when you get this sign is exactly when you see the signed normal is pointing away from the center of curvature. So here what is happening is that here the signed curvature, so let me write this here, signed curvature, and this is going to be at T naught, we are going to define it to be K S T naught. Okay, and what is the definition of signed curvature? It is written in such a way that this sign problem is fixed. Okay, so what should happen is, okay, epsilon T naught should be gamma T naught plus 1 by signed curvature at T naught times the signed normal at T naught. This equation should hold. Okay, and you have to watch this very carefully. Here I am replacing actually this term without the modulus, and therefore there is a sign, and that sign is adjusted so that this equation is always true. Okay, You must understand that if I put unsigned curvature there, then this plus may not hold, you may have a minus. But I want always write it with a plus. And that's the reason why I put a sign to the curvature. Alright. And just for later on, what will happen is if you have a space curve, you don't have to worry about signs. And the sign is kind of taken care of by the left-handed or right-handed coordinate system, and that is controlled by the torsion. Okay, so you don't have to do that. But here for plane curves, you have to worry about the sign of the curvature. Okay, if you want to use vectors, and you see why sign curvature has to be introduced. Okay, so you see this is sign curvature is positive at t naught. Okay, now you can imagine if I had the same thing. Suppose I was traversing like this. Okay, and this is the point. Let us say gamma t naught. Then you can see that the tangent vector is going to be like this. The tangent vector at t naught is going to be like this. You make what is the sign normal now? You see the sign normal will be rotate by 90 degrees anticlockwise. So what will happen is your sign normal will be like this. Okay. But but again, what happened to the circle of curvature and the center of curvature? It is the same. Right. See, the circle of curvature is still the same thing. The center of curvature is somewhere here. And you see now what is happening is that so this is a circle of curvature at t naught, and this is a center of curvature at t naught. So please don't get confused. C of t naught is a circle of curvature at t naught. C subscript t naught is the center of curvature at t naught. Unfortunately, it's somewhat confusing, but let it not confuse you. The point is that in this case, you see what is happening is that because you are traversing the same curve in the other way, the other direction, your sign normal has gone to the other direction. So it's not pointing in the direction of the center of curvature. So this is the case when the curvature is negative. Okay, so you see there are cases of negative curvature and positive curvature, and of course this is for curves which look like concave upwards. You can also have a similar situation. You can draw two more pictures. Suppose a curve is like this, is being traversed like this. Then you see, and this is the point gamma of t naught. What happens is, let me update this. So then what will happen is that now the tangent direction will at t naught will be like this. Okay, and you see the circle of curvature will be at t naught will be this, and again the center of curvature will be somewhere here. Okay, what is the sign normal? Rotate by 90 degrees in anticlockwise sense. So this will be the sign, this will be the normal direction. Okay, and you see this is going to be rotating like this, and now see what is happening. Now the normal is pointing away from the center of curvature. So this is also a case where the sign curvature has to be taken negative. And there is the other, case which is the same thing being traversed like this. And you can see now the curvature will be positive, because you see now at this point, you see now the tangent direction has become the other way. Okay. Now if I rotate the tangent by 90 degrees in the anticlockwise sense, the normal will go to the other direction, but now this is the correct direction pointing right into the center of curvature. So you see this is going to be, so this is 90 degrees, this is also 90 degrees, and this is going to be normal as at t naught, and this is really pointing towards the center of curvature, and this is a circle of curvature. Okay. And so in this case, what is happening is that this is again the case when the curvature at t naught is positive. Okay. So you get these four cases. Okay. So the moral of the story is, why this adjustment is made? Only with this adjustment you can write this vector equation correctly. The reason is because of this term here. Okay, this term here. So let me get rid of all of this. The reason is because of this fellow here. I want you to understand that. The reason is because of this term here. This is of course positive square root. This is also positive. The problem is with this term, the denominator. That can have a sign. And that, because of that sign, you have to adjust it. Okay. If you bring in radius of curvature, it should always be positive. So the only way is, if you think of curvature as inverse of radius of curvature, you have to put a sign to the curvature. You cannot put a sign to the radius. That doesn't make sense. You cannot have negative radius, doesn't make sense. But you can put signs to the curvature. Okay, and this is because of this orientation given by the signed normal. Okay, so this is what I want you to understand. So the moral of the story is, you see, we have used just simple plane geometry and ordinary calculus, and we have established that there is a center of curvature, there is a circle of curvature. Okay, and therefore you see you have got the formula for the radius of curvature. What is it? Radius of curvature at t is going to be just this expression. This is the expression. Of course, this expression is for t equal to t naught. So you remove the subscript. So r of t is just going to be this expression, x dot squared plus y dot squared to the 3 by 2 by x dot y double dot minus y dot x double dot, and I have, mind you, I have put a mod here. All right, and if you want the magnitude of the curvature, not the signed curvature, okay, unsigned curvature at t, okay, at t means at gamma t, okay. Oops. Unsigned curvature at gamma t, all right, it's going to be reciprocal of that. So k gamma t or kt or k gamma t. So kappa is the Greek letter that is used. Kappa t or kappa gamma t is 1 by RT, and you get this formula, namely it is mod x dot y double dot minus y dot x double dot divided by x dot squared plus y dot squared to the power of 3 by 2. Okay, this is what it is. So you have formulas for this. You have got these formulas. Now you see there are two issues now. I have to define. What I have done is I have taken a parametrization of a curve and I have derived all this. What if I change the parametrization? Okay, how is it that, for a different parametrization, parametrization means what? See, you have written the curve gamma t as xt yt. Okay, but I can also write gamma t as some other x1t y1t. I mean, basically parametrization is you are writing x coordinate as a function of the parameter t, y coordinate as a function of the parameter t. Different parametrizations can give the same curve. Okay, so y squared equal to 4x parabola is, you have studied, is usually at squared 2at. But I can put t instead of t I can put u squared, and I can write everything in terms of u, and it will look, the formulas will be, functions will be different. So at squared will become a u power 4, 2at will become 2a u squared. Okay, if I put t equal to u squared. So you see but just because you change the parametrization, will the curve change? It will not change. So the moral of the story is that, but these formulas, you have to make sure they don't change with the parametrization. Why should they not? Because you see, radius of curvature, circle of curvature, center of curvature are geometric things. They should depend geometric. They should be just geometry and not analytically depend on how you wrote the curve. Okay. Now, so that is one problem. The problem is that no matter how you write the curve, I should get this formula. That's the first thing. Or for that matter, if you want to say it in other words, if instead of a parametrization gamma, I put some other parametrization, I should still, the same formula should give me the same values. Okay, that's not obvious. Okay, so it should be independent of the parametrization. You have to prove that. Okay, then the other thing is, I have still not defined what radius of curvature is as a mathematical definition in a very crisp way. Okay, so that has to also be done. And you see, again let me emphasize, when I say I want to define curvature mathematically, it means that is also a definition that should not have anything to do with parametrization. Okay, all right, at least even if you define it using a parametrization in some nice way, you have to show that definition is independent of the parametrization. So you see, that's because these geometric things are independent of the way you write things analytically. They should be, right? if something, geometrically, if something is a circle, no matter how you write its equations, finally you should only geometrically get a circle. You should not get a parabola or hyperbola or something else. Okay. So that is the point. So we have to go, so we are going towards that. Okay. And the way to do it is to look more carefully into a few things, but I can tell you what's coming. See this, already this tells you something. This whole thing can be rewritten in terms of gamma. So you see, gamma is, if you write it as x comma y, I am suppressing the t, which is the variable. Then gamma dot is nothing but x dot y dot, and you can see gamma double dot is actually x double dot y double dot. Okay, and you can see what this quantity is. You can see that this quantity in the numerator is gamma dot cross gamma double dot, is actually the cross product. It is a modulus of the cross product. Okay, and what is there in the denominator is norm gamma dot to the 3 by 2. You see, you get this, or rather, no, if I write norm, I have to forget the half. So let me get rid of the half. It's norm gamma dot cube. See, remember, what is norm gamma dot? It is the length of the tangent vector. Okay, gamma dot is a velocity. Gamma dot is d gamma by dt. Gamma is a position vector with respect to t. So d gamma by dt is gamma dot. That is the rate of change of the position vector, displacement vector. So it is a velocity vector. So the velocity vector is gamma dot. The length or the magnitude of the velocity vector is the speed. So this is actually the speed. So norm gamma dot, you can see, is the length of this vector, and it will be x dot squared plus y dot squared to the 3 to the half. And the denominator I have to the half to the power of 3. So I get this. Okay. So you see, you are getting this formula. If you write it see, you are able to write it in terms of gamma. Okay. But gamma still depends on its components, x of t, y t. Beautiful thing is, the first beautiful thing is, this formula works also in 3 dimensions. Okay. Even if you take a helix, okay, this is the curvature at every point. We will show that. Okay. But to get to that, you will have to define the curvature in a nice way. So you see, this is going back to how to define things properly. Okay. So we will later see that for a curve gamma t, even in space, the curvature unsigned is given by this expression. Okay. And so maybe in the numerator I should have put, since I used vector notation, I should not put mod, I will put norm. Okay. I mean, mod of a vector is supposed to be norm of a vector, but if you stick to the fact that mod is only for real numbers and norm is for vectors, I should have put norm there. Okay, that's what I meant. Okay. So this formula is also correct. So you see, this derivation also suggests that such a formula is plausible. Okay, now we have to use vector calculus and really prove it. Okay, which we will do. Okay, now, but that's for later. But before that, what we have to do is we have to solve this issue. You change the parametrization, my radius of curvature should not change. That's one thing. The center of curvature, circle of curvature, radius of curvature must not change. That's one thing. It should not depend on the parametrization. That's one thing. Second thing is, how are you going to define curvature of a curve? Okay, without all this, without any parametrization. Or you give a definition and show it doesn't depend on the, parametrization. So far, what we have done is, we have only used some qualitative things, but thankfully you are getting formulas. Okay, yeah, you have a question. Even this formula is dependent on the parametrization. That's right. That's correct. Yeah, but you are absolutely right. So even if you write this, in terms of gamma, it still depends on gamma. And therefore, if you change gamma, whether this expression will change is not clear. That has to be established. Okay, but it will be established if you got to this expression by a definition which is kind of independent of gamma. If you could make a definition of curvature which is independent of gamma, okay, and got to this expression, then it's obvious that whatever gamma you use, you will only get this, okay. So, so these questions need to be fixed, all right. So let's go into the details for that. So yeah, you again have, yeah. So it's a it's a natural question to ask. I mean, does this tend to mean that if you the curve might have different curvatures, different circles of curvature, different centers of curvature, different radii of curvature as you change the parametrization? It should not happen, because these objects are all geometric and they are determined by the shape of the curve at that point. So they should not have anything to do with the way you are representing the curve. And so it's our job to actually show that this is indeed the case. So that is what we are going to do. Okay. So you see, so the first thing, this whole business of looking at a curve or representing a curve analytically, it's the analytic expression that you are worried about. So go back to the analytics. How do you look at a curve analytically? There are several avatars. Now what you have to do is you have to kind of reconcile all of them. Okay. So let me tell you. So you see, what are the so let me put various avatars of a space curve. I mean, let me just take a plane curve for the moment. Okay. So you see, the simplest that we all know is the graph of a function. Okay, that's a curve. So the simplest avatar that we are used to write from school, graph of a real valued function of a real variable. Okay, this is the simplest of them, and this is something that's very clear. Basically, what you do is you take some open interval on the real line, and this is the real line, and you have a, if you want, you have a t here. Okay, and usually we use x and y, so let me use x and y. So there is x here. Then you have this function y is equal to f of x. Okay, and this goes again into the real line. Okay, and then what you do is that you plot the graph of this. So what you do is you have this interval from a to b on the x-axis. Okay, and for every value x, x, you take this point with the y coordinate fx. Okay, and so you get this point x comma fx, and this is the graph, and this is going to give you a curve. Okay, so the simplest avatar of a a curve is just the graph of a real valued function. Okay, now I am going to look at this with respect to one very important property. See, when we did this derivation for the curvature, we had assumed a couple of things. First thing is, you assumed that the curve is second continuously differentiable. Okay, you wanted second continuously differentiable. That's because you see second derivatives are coming. Okay, you are getting this x double dot, y double dot, and all that. So you need the curve to be second continuously differentiable. Basically, you want it to be second differentiable, but then I told you just having a derivative of certain order which is not continuous is not going to help, because you may have to work with it. That should also be continuous. So whatever derivative order you assume exists, also assume it's continuous. So it's second continuously differentiable. That's one thing. The second thing is that you see, at every point there is a non-vanishing tangent vector. That is a velocity x dot. What is a velocity vector? If you write it as gamma t xt yt, then gamma dot t is a tangent vector. It's a velocity vector. It's going to be x dot t y dot t. What is its length? It's square root of x dot squared plus y dot squared. That should not be 0. And when is that not 0? When both x dot and y dot don't vanish simultaneously. That should not happen. So look at these 2 points. The first point is that the velocity vector should not vanish. You should have a tangent vector properly at every point. And the other thing is, of course, that it should be second continuously differentiable. You put those conditions here. What conditions on f will will give you that. You can see that the only condition that you need is that that f is second continuously differentiable is enough, that the tangent vector will never vanish is automatic. Okay. So you have a question.
Can you give an example of a curve where the tangent vector vanishes?
Okay. So these are all, we will come to that later. Okay. Yeah. So you have to look at those pathologies separately. Okay. We will look at that. We will look at that. Okay. So we will look at that. So you see, if you look at this, we need to get to define curvature. We need f is C2AB. What does this mean? This means that it means f dash, f dash, f double dash exists and are continuous on the open interval AB. And of course, where f dash is df by dx, okay, which is actually dy by dx if you want, and f double dash is d squared y by dx squared, okay, which is the same as d squared f by dx squared. All right, and so we need f to be second continuously differentiable. All right, and that is one condition. The second condition is that I want a non-vanishing tangent vector at every point. So what is the tangent vector at this point? Okay. See here what I want you to understand is that here you can take x itself as t a parameter. Okay. So this actually this gamma can be written as gamma is equal to gamma of t. You can write it as xt comma yt, where this xt is actually your x and yft is actually fx. You see that x itself is a parameter. Now what is gamma dot? Gamma dot will be d by dt, but t is x, so it's d by dx. So if you write gamma dot, you will get 1 f dash. Okay, and therefore what is the will this ever vanish? Never, because there is a 1 there. You see, therefore norm gamma dot will be root of 1 plus f dash of x the whole square. It's never 0. So you see, it never, there is no, the tangent vector never vanishes. So it's a nice situation. And for this parametrization, okay, with this as a parametrization, you apply our original formula, you will get the formula for curvature of the graph of a curve y is equal to fx. Okay, so all you have to do is just plug it in. So you see radius of curvature at x comma fx will be what? This is just this is just this formula. It's x dot y double dot minus y dot x double dot. So let us write this or yeah, whichever way you want. Let me write it for the curvature. So curvature at x comma fx for gamma, okay, is going to be, what is it? Is going to be gamma dot cross gamma double dot norm by norm gamma dot cube. Okay, so you see norm gamma dot is this, and gamma dot is 1 f dash x. Gamma double dot you differentiate again with respect to t, but t is x, so you are again differentiating with respect to x, so it is just 0 f double dash. Okay, and what is the cross product of this? If you write the cross product, I will get, so the only thing that will work out is the last column. So I will get k hat into f double dash. That's all I will get. Okay, that's right. And therefore norm gamma dot cross gamma double dot is going to be, norm of this is just modulus of f double dash x. Okay, and therefore this is going to be just modulus of f double dash of x divided by cube of this fellow. So 1 plus f dash of x to the power of 3 by 2. So that is a formula for curvature. For your good old graph of a function, okay, which is second continuously differential, here is the formula for curvature at a point for that curve, for that graph. Okay, so you get it. All right. So this is one. So you see, this is a very nice situation. Here you can directly apply the formula for curvature, everything is fine because it is, you assume second continuously differentiable and the velocity vector never vanishes. Okay. Okay, now, but if you want to do it for a general parametrization, as we did it, you have to assume, in addition that the parametrization is second continuously differentiable, you have to assume that the tangent vector never vanishes. Okay. There is yet, so the second avatar is going to be just parametrized version. Okay. You see, the second avatar is a parametrized version, but parametrized version anyway we have seen. So what happens in the case of the parametrized version is, you see, what you are doing is you are taking image of a function which is different from graph of a function of a real variable. Okay. See, in the parametrized version what you are doing is you are going from, your gamma is now going from AB to the plane. You must understand. See, this is different. When you say graph of a function, the function is going from the real line, a portion of the real line back into the real line, and you are drawing its graph. So the points are x comma fx. The graph of a function is real valued function of a real variable is a curve. But if you see it as a parametrization, that function, that parametrization is actually not a function on from the real line to the real line, or a portion of the real line to the real line. It's actually into the plane. So if you write it as gamma, this is t is going to gamma t, and now gamma t has got two coordinates, is x t, y t. And therefore, when you say parametrized curve, you are actually looking at the image of gamma. And the other word that is used is trace of gamma. That is what gamma t traces as t moves in AB. So you see, therefore, what you are going to get is you are going to get something like this, and this is called, you also write this as gamma t. This is this curve is nothing but the trace of gamma. It is also called the image of gamma. And by abuse of notation, you simply call it gamma itself. So gamma is also the curve, gamma t is also the point, gamma t is also the position vector. So there are so many parallel ways of thinking about it. All right, but notice that this is from the from an interval on the real line into the plane. This is different from the graph of a real valued function of a real variable. Okay, and in this avatar, of course, we have already made the derivation. You need gamma to be second continuously differentiable, and you need that gamma dot never vanishes. Okay, so need for defining curvature that gamma is C2 in AB. This is the same, it's second continuously differentiable. That means both the xt, yt should be second differentiable in t, and the second derivatives must be continuous. That is x double dot t, y double dot t, they must be continuous. All right. Then the other important condition is gamma dot never vanishes. And you know why this gamma dot never vanishes? Because see, you are working with normals and tangents. Okay, this normal slope and the tangent slope is y dot by x dot, normal slope is minus x dot by y dot, and you should not divide by 0. At least one of x dot or y dot should not vanish. Okay, then there is a third avatar. Okay, and that third avatar is writing a curve implicitly. Okay, so I can also write a curve as x squared plus y squared equal to 1, for example. It is a circle. It's a unit circle centered at the origin. So there is a third avatar of getting a curve, and that is what is called the implicit function method. Okay, so let me write this. So third avatar. Okay, what happens is that write the curve using an equation. Simply example, x squared plus y squared is equal to 1 is a circle centered at 0, 0, radius 1. So here what is happening? Here something else is happening. What is happening is that you are taking a function of two variables and you are taking what is called the level curve. Okay, there is another way of getting a curve. Writing the curve as an equation. If you have an equation, one function equal to another function, you can juxtapose everything to one side, bring everything to one side, and simply write it as one function equal to 0. But one function equal to 0, that function will be a function of two variables. Okay. Now, this function of two variables equal to 0 is as good as this function of two variables equal to constant, because that constant can be pushed to the left side. So basically you are looking at a function of two variables equal to constant, but that is exactly what is called the level curve of a function of two variables. Okay. So yet another avatar of looking at a curve is looking at it as a level curve of a function of two variables. Okay. So this is exactly looking at the level curve of a function of two variables. Okay, example, you take fxy is equal to x squared plus y squared. Okay, then this function f is going to go from r2 to r. Now you see the function has changed. Okay, you just see the way the curves are written. There are different avatars. The first one was graph of a function which went from a portion of r back to r. That's a graph of real valued function. The second one is parametrization, which went from r to r2. Okay, and the third one is the other way around. It is going from r2 to r, but you are looking at level surfaces. In this case, it's level curves. Had it been function of three variables, you will get a level surface. Okay, and why this point of view is important? Because then multivariable calculus will come and tell you that you get the normals by looking at the gradient, and existence of the normals will be equivalent to existence of the tangents. Okay, and therefore the gradient will enter. Okay, and the gradient is anyway the first derivative. Okay, so you see again it's kind of the velocity on the curve, and therefore this condition that the velocity should never vanish will put the condition that the gradient can never vanish. Okay, because the gradient will give you the normal direction to the level curve, and the gradient vanishing is exactly the condition that you get a singular point. Okay, so that is how you get singularities. So what you understand is that you are able to get curvature for a curve whenever there is a regular point. All right. So let me just write this looking at level sets. Here this is level curves. F is equal to constant, gives circles, constant positive, x squared plus y squared is equal to constant positive. Okay, so this is the third avatar, and whatever your definition of curvature is, okay, it should work for all the avatars. It should be universal. All right, and let me conclude by just saying something. You can move from the third you can move the third avatar to the second one. Okay, by a device which is called the implicit function theorem. So here is where some analysis has to come in, some analysis in topology. Okay, this is rather a serious issue. There's something called the implicit function theorem, okay, which will tell you that if you ensure that the gradient never vanishes, at every point where the gradient never vanishes, your level curve will look like graph of a function, okay, locally. And the graph of a function can be parametrized by the independent variable. That's what I have already told you. Okay. So therefore you can, all the three avatars are actually, you can move from one to the other. And the only condition you need is that you need this thing that in the level curve case, the gradient should not vanish. That is equivalent to, in the curve case, the velocity never vanishing. Okay. And what we are going to do is that this is what we are going to call as regularity. And this is exactly the same as the curve having a proper tangent at every point, a continuous tangent at every point. Okay. So there is going to be an analytic regularity, there is going to be a geometric regularity, and they are both the same. Okay. So you have to bridge and reconcile both the analysis and the geometry. Okay. So I will stop here, and we will continue in the next lecture. Okay.